All right, for this lecture, we're going to start chapter 3 of the book. Why do they call it head over heels in love if our head is always over our heels? Can a hearse driver drive a corpse in the carpool lane? Why is the name of the phobia for the fear of long words whatever that really long word is? How do they get those boats in those glass bottles? Why would Superman want to leap over the tallest building in a single bound if he can fly? Why is it called a TV set when there is only one? If it's 0 degrees outside today and it's supposed to be twice as cold tomorrow, how cold is it going to be? How did the Headless Horseman know where he was going? Why do they call it an escalator to escalate if it takes you down? Why is it called a football when you hardly use your feet? How come some Little Debbie snack cakes come in a twin pack and others are wrapped individually? Can a guy named Nick have a nickname? If a person owns a piece of land, do they own it all the way down to the core of the earth? What is a male ladybug called? Why are semi-trucks bigger than regular trucks? How fast do hotcakes sell? Why are they called stairs inside but steps outside? Does the president have to pay taxes? Why do they put for indoor or outdoor use only on Christmas lights? Is there really another option? If Dracula has no reflection, how come he always has such a straight part in his hair? If an ambulance is on its way to save someone and it runs over someone, does it stop to help them? Why is grape nut cereal called that when it contains neither grapes nor nuts? If Jimmy cracks corn and no one cares, why is there a song about him? Since running back runs forward, why is he called a running back? If an atheist has to go to court, do they make him swear on the Bible? And lastly, why do they call the small candy bars the fun sizes? Wouldn't it be more fun to eat a big one? Alright, real biology for today. Organic chemistry. We've kind of gone through chapter 1 stuff, chapter 2 stuff, but now we're going to get into chapter 3, organic chemistry. Seriously, one of my favorite classes in college when it came to chemistry. OChem. Sometimes it's considered to be one of the more difficult classes, but this is the point in time where chemistry actually started to make sense for me because it really applied to the biology classes that I was taking as well. A couple definitions I've seen of organic chemistry. If something's organic, I've seen it saying that it contains both carbon atoms with hydrogen surrounding them. I've also seen it called, organic chemistry, one or more elements covalently bonded to carbon atoms. Oftentimes one of those is hydrogen, that element. Some characteristics of carbon. Carbon is going to be the basis of all of our organic chemistry, and a couple characteristics would include 4 valence electrons. So over on the picture on the side here, you can see in this inner shell you get 2 electrons, and this is carbon. It has 6 protons. So we've got 2 electrons and then 4 more to be the 6 electrons to balance out the 6 protons. So it has 4 valence electrons. Since it has 4 valence electrons, it then wants to make a covalent bond here, 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 and here for a total of 4 covalent bonds. So that makes it quite versatile that it can make 4 covalent bonds. Not all molecules can do that. Carbon also has what's called a tetrahedral structure. If you look at the bond angle between the carbon, anything else bound up to it, those 4 covalent bonds that it makes, it has 109.5 degree bond angles, and it would look a little something like this. And so this is trying to show us 3 dimensions in a 2-dimensional PowerPoint. But you can see the hydrogens, 2 of them are pointing away, 1 of them up, and this one's pointing actually down and towards you. So it kind of sits up a little bit on a tripod with 1 hydrogen going up. And no matter which way you angle it, it'll always take on that shape, with 1 going up and then this tripod of hydrogens going down towards the base. A common question that people ask, especially scientists, is why is carbon used as kind of this building block of all life and not something like silicon? Because if you look at the periodic table of elements, silicon is actually right below, along with some others, right below carbon. And so all of these have the ability to make 4 covalent bonds. So why is it that life chose carbon and not something as simple as silicon right below it? since they're all basically the same type of molecule in terms of what they're capable of in terms of covalent bonds. And a simple answer, a book answer, is because covalent bond strength is inversely proportional to atomic weight. So if we look again at this picture here, atomic weight of silicon is more than twice as high as carbon. And so if it's inversely proportional, covalent bond strength is inversely proportional to atomic weight, this right here, carbon, at the lowest atomic weight, actually would have the strongest bond. And so nature has chosen, probably due to some sort of natural selection type properties, nature has chosen the strongest bonds of which to build life. Carbon also has the ability, because of its versatility and four covalent bonds, has the versatility of forming chains, branching chains, and rings. What do I mean by that? Well, on this slide, it talks a little bit about the term hydrocarbon. When we were playing around with the molecular magnetic water kit, we had carbon connected up to carbon, and it was actually surrounded by, in all cases, hydrogen on each side of it. And I'm still learning how to use this writing pad that I'm using here, so I apologize for the sketchiness of this, but for those of you that know in class, it's not a whole lot different when I'm writing on the board. So this is some carbon atoms surrounded by some hydrogens. That's a carbon backbone, and so that term carbon backbone is there. And we have hydrogens attached to it. Carbon backbone, the base of this molecule, surrounded by hydrogens, has a fancy name. It's called a hydrocarbon. We built that, and we saw that it was very non-polar in nature. And we saw that water molecules, which were polar, were not able to stick to that using those polar hydrogen bonds. And so these hydrocarbons, very non-polar in nature, but at the same time very versatile. So here we have a simple methane group. Maybe in chemistry class you learned a little bit about methane as CH4, carbon surrounded by hydrogen. Some scientists call this the simplest organic molecule. You can then pop off one of the hydrogens and you get what's called a methyl group. You can take another methyl group and attach it together and you get ethane with two carbons surrounded by hydrogen, what I drew over here on the side. Pop off a hydrogen, you get an ethyl group, and you can obviously continue to add carbons like you see down here at the bottom, building a continuous chain of carbons surrounded by hydrogens, and you get this long, straight, linear hydrocarbon chain. We're going to see some of those as we continue on working with things this chapter. That hydrocarbon chain has the ability to then make branches. You can get a branching hydrocarbon chain off of a hydrocarbon chain. Again, more versatility. And if you would take a bond here and fold it in on itself and bond it up to another carbon, you can actually get a ring of carbons surrounded by hydrogens. We're going to see that as we start working with some carbohydrates in the not too distant future. Scientists that get lazy sometimes will draw it like this carbon ring, just as a hexagon in this case, and each of the points represents that there is a carbon there and that it's surrounded by other things. We know that because each of these points could make four covalent bonds like we see kind of over here, 1, 2, 3, 4 off of each of those carbons. But this is, as you get into heavy-duty organic chem, you're going to start trying to find ways to shortcut your drawings and stuff like that. That's a common one. You could even go further and take those carbon rings and attach them to other carbon rings and get big, long chains of carbon rings. And by golly, if you're guessing it, you could even make branching chains. Just like we had a branching chain up here, we could have a branching chain of carbon rings. And again, we'll see some of those as we get through this chapter. The last one is that you can get carbon to form both or all single, double, and triple bonds. And what I would expect you to know about this is a little bit about bond strength, bond length, and a little bit about the motion. So if you had a single carbon to carbon bond, this tends to be the longest bond, meaning the distance between one carbon to the next would be the greatest distance. It's a very small measurement, but it is the longest of the three options. You obviously said we could bond up to 4 things to these carbons. So one is carbon to carbon, but you could have in this case some hydrogens around it, as well as a variety of other things. And those, because this is just a single bond here, that whole structure would have the ability to rotate up and around and around and around. It could actually spin on this single bond. So around a single bond, other things can spin around it. And when it comes to actual strength, out of the three options, this is a relatively weak covalent bond because 1 is not going to be as strong as 2. Well, if I would move on and draw something similar, and I'd make a double bond here. Now each of these carbons has used up 2 of its bonds, so it technically only has the ability to make 2 other bonds. In this case, because there are 2 bonds here, it's going to bring it together a little bit. The overall distance between carbon to carbon is going to be a little bit shorter than the single bond. It also is not going to have the ability to spin. It could flex back and forth a little bit. You might be able to get it to flex this way a little or get it to flex that way a little, but it will not be able to spin because the double bond kind of starts to lock it into place just a little bit. And when it comes to strength, obviously 2 is stronger than 1. Now lastly, what we would get is a carbon to carbon 1, 2, 3 triple bond. So they're going to be sharing 3 pairs of electrons, and now each of these can only make 1 more bond. Only has 1 more open binding site for that 4th covalent bond. This is going to be the shortest of all of the bonds. The carbons are going to be quite close together. There is a lot of strength here. 3 is stronger than 2, which is stronger than 1. And when it comes to actual motion of that bond, it doesn't bend, it doesn't flex, it doesn't spin. They're going to be locked in place, carbon to carbon. Now this hydrogen out here is on a single bond, so it would actually have the ability to spin around itself on that single bond, but the triple bond here would be locked in place. So that's a little bit about the relative strength, relative length, and a little bit about the motion of those single, double, and triple bonds that are being able to be made with carbon. Another important characteristic that we see commonly found in organic molecules is the term isomer. The term isomer, if you know a little bit about root words, the term isomer does have some meaning. Let's see if I can get my pen to work here. Here we go. Iso means same, if you ever see iso at the beginning, and mer means unit. So isomer means same units. And so these are two molecules that have the same units. And if we look at them a little bit more closely, where am I? I'm up there now. If we look at them a little bit more closely, we can start counting some of the atoms. This has 1, 2, 3 carbons, so it's got 3 carbons, and if you look at count them, it's got 6 hydrogens and 3 oxygens, and so we could possibly write that C3H6O3. Over here, this dihydroxyacetone has also C3, count them, H6, and O3. If we look at their actual molecular formulas, they are absolutely the same molecular formulas. But if we look at their structures, they are not the same structures. They've highlighted for us the double bond, and this one is on the 3rd carbon in the chain. If we count from left to right, 1, 2, 3, the double bonded oxygen is on the 3rd carbon, whereas this one is on the 2nd carbon. And it's kind of like Legos. If you have building blocks, certain number of Legos, certain color, certain one with 4 connectors, and some are 2 and some are 1, and you can build something out of it. Like my son, for example, he might build a pirate ship out of Legos. But my daughter, she comes along and sees those same Legos and she says, I'm not looking at to have a pirate ship. I'd like to build a princess castle. Is it possible for her to take apart the pieces of that pirate ship, use the exact same pieces, and instead build a princess castle? Well, possibly yes. And so I like to think of isomers as that kind of thing, where you can take Legos and turn them into something completely different using the exact same building blocks. And so by definition, an isomer is when molecules with the same molecular formula, the same building blocks, are used to make different structural formulas, have different structures. And in chemistry, a different structural formula may have a very different function then as well.